Good afternoon and welcome to Hydromantis webinar. Today we will be talking about modeling chlorination process in GPSX. My name is Rajiv Goyal and I'll be showing you through this chlorination model, and I have my colleague Spencer Slalling with me here who will be telling you something what's new at Hydromantis later on. So first of all, looking at the agenda, we'll be talking about a little bit on the introduction side, giving you a little bit of a background of this chlorination model, also talking about chlorination reactions and some of the byproduct formation model that we have included in the model. Finally, I'll be giving you a model demonstration to acquaint you with the new model in GPSX. A couple of months before we released our new version, GPSX version 6.5. And here are some of the things which are new in GPSX 6.5. MABR model, which is a membrane aerated biological reactor model. This is a model we put together in 6.5 in collaboration with the GE. The other model that we included is the blower head loss model. In the aeration systems, the piping, there are head losses in the pipes, diffuser pipes, diffuser head losses, and the pipe head losses. So they are calculated in this model, and based on which we can calculate the energy of the blower in a more appropriate way. There are some other models like advanced oxidation process model, chlorination model, on which we'll be talking today. Some of the advanced controllers we have included, and energy diagrams and enhanced optimizer. So if you have not had a chance to download 6.5, please go ahead and download 6.5 and experiment with all this new stuff that we have included in version 6.5. Coming back to our topic of today, chlorination. So most of you are familiar with chlorination process. It's mostly used for disinfection process, to disinfect, basically disinfection process, and control the pathogens in water and wastewater. So most of the time we will see that the wastewater which are coming from the treatment processes, they need to be reused or they need to be applied in the land. So in those cases there are some regulations with respect to the pathogens that or the limit on the pathogen quantities that can be discharged in such applications. So chlorination is a preferred method because of the low cost, odor control, and the effectiveness that chlorination provides. On the other side, there are some of the drawbacks. For example, it can lead to byproducts formation, especially when there are dissolved organic matter in the water. It can lead to production of trihalomethanes, which are actually genotoxic, or which can have mutagenic effects or carcinogenic effects, and can cause adverse ecological and health effects. So that's why it is necessary to control the production of the byproducts that are formulated during the chlorination process. So when we are looking at the objective of chlorination, we want to achieve good disinfection. At the same time, we want to control the production of the disinfection byproducts and minimize the dosing. So there are multi-criteria objectives in the chlorination process, and it's kind of useful to have a model that can predict the chlorine residuals, estimate the disinfection byproduct formation potential, and also estimate the disinfection efficiency. So this is something that we wanted to model for a project that we were doing last year, and the outcome of that project is the model that we are going to demonstrate today. So first of all, looking at the chlorine reactions in wastewater, there are, as you can imagine, there are several compounds in wastewater which can react with chlorine, and most important of them are one is the ammonia, organic nitrogen, and these two compounds can react with chlorine and can formulate chloramine. Also, there are BOD, COD, and TOC compounds, which are the organic compounds in wastewater, and water, they can react with chlorine and formulate trihalomethanes or haloacetic acids. So these are two of the major byproducts that can be seen in a chlorination reaction. There are other reduced compounds which can react with chlorine. For example, iron, hydrogen sulfide, they can react with chlorine and can form oxidized inorganic compounds. The other important parameter in chlorination is the alkalinity of the water, because we are adding chlorine, and depending on in what form we are adding chlorine, it can lead to a reduction in the pH. So in that case, there is a need for having proper alkalinity in the water. So today we are going to talk about most important reactions, which are the reactions with ammonia and with respect to the organic carbon that is present in the water. So looking at the reactions with ammonia, these are very well established reactions. So chlorine can react with ammonia and can form monochloroamine. And if we have excess chlorine in the water, then it can formulate dichloroamine. Also, if we add more chlorine, then dichloroamine can react with chlorine further and can formulate trichloroamine. And then finally, the nitrogen can get oxidized to nitrogen gas by chlorine. So essentially, for a complete reaction of ammonia oxidation, if we want to write with chlorine, then in that case, this is an overall reaction, in which case we know that 1.5 mole of HOCl are required to completely oxidize ammonia nitrogen to nitrogen gas. So when we look at the implication of these reactions, and since we are talking about wastewater in which we can expect quite a lot of ammonia coming out in the effluent depending on the treatment process, we are looking at this kind of a diagram, which is it's a diagram which shows the chlorine to ammonia ratio and how the nitrogen concentration and the free chlorine residual that is can be seen in the reaction. So in this particular case, we can see that when we increase the chlorine to ammonia nitrogen ratio, there is zone 1. In the zone 1, all the ammonia is getting reacted with chlorine to form monochloroamine, and there is a stoichiometric ratio. So if the chlorine to ammonia ratio is 5.07, less than 5.07, we are in zone 1, and most of the chlorine ammonia will get reacted to chlorine and form monochloroamine. If we add more chlorine, if the ratio increases to more than 5.07 and less than 7.58, then some of the chlorine starts to get converted into nitrogen gas, basically trichloroamine, and complete oxidation of ammonia starts to happen, and we'll start seeing reduction of nitrogen concentrations here. So at the point when all the ammonia is oxidized, barring some, we come to a kind of a minimum point here, which is called the breakpoint chlorination. And after that, we can see that the ammonia or the nitrogen concentrations are stabilized, but on the other hand, the free chlorine residuals have started to increase. So in zone 1 and zone 2, we can expect that chlorine is combined with ammonia and it's a combined chlorine residual. On the other hand, after breakpoint chlorination, we can see a free chlorine residual that starts to appear. This is really important in modeling because based on the literature, chloramines, free chlorine has a higher potential of producing disinfection byproducts as compared to combined chlorine. So in some situations, we want to operate in zone 1 or zone 1 most of the time, so that we can reduce the potential of formulation of disinfection byproducts. And as the chloramine is a disinfectant also, it can lead to some disinfection efficiency, but reducing the potential of disinfection byproduct formation. So this diagram is really important, and this is one of the key thing that was required to be done in the model. And so in the model, depending on the ratio of the chlorine and the ammonia, we would like to generate this kind of curves in the model. Now, as I said, some of the chlorine, depending on which zone we are in, some of the chlorine will be combined chlorine, which is monochloramine, dichloramine, or trichloramine. So that's the combined chlorine, which also has a disinfection efficiency, but it is not as potent as free chlorine, which is hydrochlorous acid and OCl ion in the system. So we define free chlorine and combined chlorine, and then the total residual chlorine includes the free chlorine plus the combined chlorine in the system. So coming to the second part of the thing, which is related to the formation of trihalomethane formation, we looked at different literature sources in the literature and tried to look at some of the appropriate models that can be used for predicting the formation of trihalomethanes. As we all understand, this is a very complicated reaction, and the science is very complicated. So it's a little bit, most of the models that we found are mostly empirical in nature, which are based on the relationship with respect to TOC, soluble TOC, UV absorbance, ammonia concentration. So it does take into account these parameters or these variables in the model, but they are mostly empirical in nature. Some of the models which are kinetic models that are available in literature, we looked at those as well, but in this particular implementation we tried to go with the empirical relationship. So the model that we use for the trihalomethane formation is originally developed by AMI based on a large number of studies that they conducted on different on different type of waters, and by varying the TOC concentrations, chlorine dose, retention times, temperatures. So it was a very extensive study, and they used regression analysis to come up with this kind of relationship shown in this particular equation. And of course, here we show some of the exponents which are there, and these are the GPSX model variables, but there are some default values that we have used in our model to start with. But user has the flexibility depending on, for example, the source of the TOC, the nature of the TOC. Maybe the exponent values are going to be a little bit different than the default values, and there's an option to change those parameters in the model. So as we can see, the model really depends on the TOC concentration that is there in the wastewater. Also, it depends on some of the one of the parameter which is actually reflective of the aromacity of the organic compounds, UV254. So it depends on that, the TOC concentration, the chlorine concentration, residence time, temperature, and the pH, and the bromide concentration in raw water. So it kind of takes into account most of the important parameters that can affect the trihalomethane formation potential. Now we talked about the combined residual chlorine, which is chloramine type of residual, and the free chlorine. So as I said before, based on some of the studies, it appears that the combined residuals actually have a lower potential to form trihalomethane formation. So in the model, we have considered a factor of 0.2 in the case when there is a combined residual, then the production potential for the trihalomethane is taken as 20% of whatever is proposed by this particular relationship here. Now, another important byproduct that is generated in the chlorination process is a haloacetic acid, and there are three relationships which are also of very similar nature as we had for the trihalomethane potential. Again, these relationships are coming from Amy's work, and these relationships are used to predict the monochloroacetic acid, dichloroacetic acid, and trichloroacetic acid concentrations. Again, the exponents values are taken from the published relationship, but they are the variables in GPSX model, and the user, depending on the data that they may have, can change and further calibrate the model that is that is the default model in GPSX. So next component of the chlorination model is the chlorine decay, and there are several published relationships which are available. Some studies suggest that it's the second order decay model. Some studies suggest that it's the first order reaction rate equations. So for this particular model, we have used first order relationship, and we are calculating based on the provided dose. We are calculating the residual of chlorine based on an decay coefficient of the chlorine which is provided in the model. Now the disinfection model again comes from the US EPA surface water treatment rule. It's almost very similar to the format of the Chick and Watson equation. Only thing is the coefficients are given here. So this is the equation that has been used, and based on the coliform counts which are provided by the user in the model, depending on these conditions, we are estimating what is the log inactivation rate for the coliforms. Now, some of the two things basically which normally are not available in activated sludge models is the TOC and the UV254. So for estimating TOC, we have the relationship based on the CODs that are there for the soluble substrate, for acetate, for propionate, methanol, and SI. We have some standard relationship because the CODs for each one of these are known. And the carbon content of each of the specific compounds are known, so we can estimate TOC based on the carbon content of each of these compounds. For estimating the UV254, we use the surrogate compound SI, which is a soluble inert compound, and try to have a linear relationship between SI and UV254. So that's the way we calculated UV254. So in the case of activated sludge model, if the SI concentrations goes up, we are assuming the value of UV254 will also go up. So now showing you some of the outputs from the model. So as we talked about initially, the chlorine and ammonia ratio, and what kind of curves do we expect. So this is the typical output that we would expect, and on the left hand side we are showing you a typical simulation output or a sensitivity analysis output in which we have changed the chlorine dose, keeping the ammonia concentration same, and in this case we can see that the chlorine residual basically as chloramine goes up, then it goes down, and after that the free chlorine starts to appear in the system. Same with the ammonia concentration. So ammonia concentration or the nitrogen concentrations remains the same, but after that they starts to decline, and they are the minimum at the breakpoint chlorination and staying the same after breakpoint chlorination. So this is a typical graph that we generated by the chlorine dose sensitivity analysis. So in this case, when we increase the chlorine dose, we can see the total trihalomethane formation potential milligram per liter in the initial range when most of the chlorine residual is in the form of combined residual. The formation potential is low, and when the free chlorine residual starts to build up, the trihalomethane formation potential starts to increase. So this kind of curve is there are some significant number of studies that has been done by Yang et al. On the breakpoint chlorination and how the total trihalomethane concentrations change in the system, and this kind of curves are pretty similar to the observations that have been made by this particular author here. Also, we try to use the model on one of the wastewater treatment plant from which we had the data. And this is the project I mentioned initially we were working on. So this is a plant, Rios water reclamation plant at Pima County. And there are chlorination tanks which are available on the east side, west side with some specific volumes, and the average theoretical residence time of 25 minutes based on the design flows that the plant is experiencing. So we were lucky to have some data on this plant for 3 days. So in this particular case, this shows the chlorine concentration that is being fed into the final effluent, and the square marks here shows the residual chlorine that is measured at the plant. The solid line shows the model outputs. So we can see some variations, but most essential thing is that that we are from a dose of 15, we are able to predict a residual of around 2 for this particular plants. Similarly, for the east side, the chlorine dosing and the measured residual and the simulated residual in the plant. So in this particular case, most of the calibration parameter was the decay rate for the chlorine. That was the most important parameter, and still we are looking at some more data and trying to further see the validity of the model and the decay equation there. So in this particular case, this is they have been at this particular plant. We are also measuring the total trihalomethane concentrations, and again the solid squares are the concentrations that are measured at the plant, and these are the simulated outputs. So again, there seems to be some variability in the measured concentration. The model kind of shows a very some variation, but not as drastic as, or not as variable as seen in the plant, but pretty much in the same range that are observed in the plant. And in this particular case, the most important parameter that we had to adjust was to provide a relationship constant between the UV254 and the SI, the soluble inert COD in the model. And with that, we were able to kind of match the performance at the plant with the model. Now, in summary, the chlorination model that we developed is based on mostly empirical relationships that are published in literature, as well as some of the kinetic relationship, especially with respect to the chlorine decay. The model output, when you start using it, you will be able to see the chlorine residuals in the combined form or the free format, and also it can show the byproduct formation potential in the wastewater. So two of the most important model calibration parameter, in addition to the exponent that you will find in the empirical relationship parameters, for example, exponents in the empirical relationship, because the wastewater properties might be different from plant to plant, so there might be some adjustment that might be necessary, and also the relationship between UV254 and the soluble inert organic concentration that we have, and the chlorine decay rate. So these are the three important parameters that we used in the model calibration. As I said, further we are looking at 4 more data sets for further validation of this model. The model can be used for optimization of disinfection process, for reducing the chlorine dosing, and also to study the effect of whether it is a combined residual, whether it's a free chlorine, and to minimize the formation of the disinfection byproducts. So we hope that you'll be able to use the model and provide us some feedback on the model, your experiences with the model. So some of the references here we have, like I said, the AMI, this is the most important paper, I think, which has been used as a basis for several of the EPA guidelines, and it's published in 1987. Also, some of the important paper with respect to chlorination, like Dharamraza, which is based on the chlorine residual decay. and also some of the other studies that have been provided, like US EPA and Son et al. Here. With respect to the wastewater, there are some recent papers that have been published, 2012, Watson and Tang and Krasner. So most of this paper provide quite elaborate treatment of disinfection byproducts, but not necessarily dealing with any kind of modeling exercises. So, so if you have further interest, you can look at these models. So I'll just give you a very quick demonstration of the model itself, and then I'll hand it over to Spencer there. So, so first of all, this is a very simple wastewater treatment plant in which we have an influent activated sludge treatment, clarifier, followed by chlorination. So the purpose of this exercise here is to show you basically how we can estimate those graphs. So in this particular case, what we are trying to do is we are changing the chlorine dose from 0 to 10 while keeping our ammonia concentration same, or the ammonia concentration that is coming out from the influent same, and trying to see how the potential for formation of trihalomethanes changes with the dosing. So this is first of all, I think we are looking at the graph in which we are looking at the free chlorine residual, total residual, for example. This is a total residual, and most of it is a combined residual, so they are overlapping here. And after that, of course, the residual drops, and the free chlorine residual starts to go up. This is the total ammonia concentration here, stays the same, then it drops and stays the constant here. So this is a kind of a typical output that we would expect when ammonia is constant and we are increasing the chlorine dosing. So difference between chlorine dose, which is this amount, and the residual here is the amount that is decayed in the system. So this difference between these two actually amounts to the differences of the decay of the chlorine in the system. Again, when we are in this phase, basically, then we can look at our total trihalomethane formation potentials here. So we can see it's slightly increasing as we keep on going up, as the residual is increasing, and then it decreases, and then we kind of, as our free chlorine residual starts to increase, then the total trihalomethane potential formation potential starts to increase. So this is a very typical output, and this is the plant that we use to actually use the data from the full-scale plant. We use the data from the affluent that is coming out from the plant, and some of the dosing information with respect to how much chlorine is being dosed on the east side and the west side, and then trying to simulate the performance with respect to the residual chlorine and the total trihalomethane formation potential. So in this particular case, you can see we are feeding all the data with respect to ammonia, nitrogen, influent flow, chemical feed rate, and local temperature, and the pH in the chlorine contact tank for both of these reactors here. And on the right hand side, when we look at the total chlorine that is fed to the system, and the residual that is available. So this is the total residual that is available in the system. So we can see the model kind of, although as I said, there is a little bit more variation in the model here with respect to the chlorine residual than that is observed at the plant, but similar kind of trends. Also, the data that we had for the trihalomethane is shown here, and we can see that the model is kind of predicting a very kind of almost like a very small variation in the predictions there, but very close to the one that are being measured here. So, so I guess with that, I think I would like to close my presentation here and hand it over to Spencer to give you some more information about what's coming up at Hydromantis.